Well, welcome to this module number 6 of the RISE 101 module series. My name's here Griffiths Atungulu. I'm the director of Arkansas Rice Processing Program. I'm an associate professor and an agricultural engineer. My area of expertise is in grain processing and post-harvest systems engineering. I'm housed here in the Department of Food Science with the University of Arkansas System Division of Agriculture. In this module number 6, we are going to delve into rice drying methods. I'm going to describe to you the common drying methods, and then I'm also going to describe to you some of the alternative drying methods that are brought about to us because of various needs within the industry to improve on the common drying methods. Now, to begin with, rice drying methods can be classified into two broad categories. We have the traditional systems, and we also have the mechanical systems. Now, I'm not going to spend a lot of time to discuss the traditional systems. Most of these traditional systems are those systems that do not involve any mechanization or any manipulation of the air conditions. A majority of these include things like sun drying. They are primarily utilized in some of the developing countries. In the United States and many other developed countries, they utilize mechanical systems for drying rice. And these mechanical systems, they vary broadly in terms of complexity and also the capacity that they can dry rice at. They can be used on-farm and off-farm. They can be broadly classified as low-temperature dryers and high-temperature dryers. I want to start by describing some of the low-temperature dryers. As you'd imagine, for maximum quality preservation, gentle drying of rice would be ideal. And so I want to start by describing to you what we call the natural air in-bin drying system. This is most common on-farm drying method that is available, particularly within the United States rice drying areas. And in these systems, the grain bins are filled partially or sometimes completely with rough rice. And because they are using natural air, there's no manipulation of the conditions of the air, because they're using the natural air, the typical drying rate is very, very slow. And the drying within these bins can take 2 to 4 weeks, and sometimes even longer, depending on the air conditions. What happens in these bins is the natural or the ambient air is blown through the grain that is placed in the bin, and as it comes through the column, it passes through the grain, and it picks out moisture. The drying front moves from the bottom all the way to the top. The tendency is for most of the grain at the bottom to be dried faster compared to the grains at the top. And because of that, these systems can present some of the challenges like discolorations of the grain on the top, or sometimes development of hotspots depending on the prevailing ambient conditions. Now, to be able to overcome some of the demerits that are associated with natural air drying, sometimes we can slightly heat that air to higher temperatures and thereby try to improve the drying rate. And so we have what we call slightly heated or low temperature air drying systems. So in this case, just like in the natural air drying systems, the bins are filled or sometimes partially filled with the grains, and then air with little heat is added. And when I talk about little heat here, we are talking about raising the temperature of that air from ambient conditions by about 10 degrees Fahrenheit or so. And then that air is allowed to move through the grain as it's being forced by fan systems. In most of these systems, electricity is being used as a source of the thermal energy, but we also have some cases where we have gas-fired burners installed in these bins. And now, there's been a lot of technology improvement in on-farm in-bin drying systems. And so I'm trying to present here a modern bin with moisture sensing capability. What this does is we have cables that are installed within the bin, and on those cables we have sensors that have been calibrated to pick the temperature and relative humidity of the air that is closest to them, and with that information we can be able to calculate the moisture content of that grain. Now, several of these cables can be installed within this bin, and that allows us the capability to monitor the moisture content within the grain at various locations. We can monitor the moisture content in the bottom layers, the mid layers, as well as the top layers. In addition, we also have temperature cables that are installed within these bins, and those temperature cables help us to detect early enough if there's any hotspots that are developing within these bins. These sensor cables have these sensor nodes placed about 4 to 8 feet apart, again depending on the size of the bin. How do these work? Now, each of the bins have a weather station, and that weather station will pick information on the temperature and the relative humidity of the ambient air. And with that information, we can determine what the equilibrium moisture content of the rice at those conditions would be. Now, that information is picked for each node on the cable, and it can be plotted on a graph that can be visualized or be seen by the grain operators. As you can see in this figure here, you can see the moisture content profiles. And again, the top profile there is showing you the node that is placed at the top of the bin. As you can see, it takes prolonged period of time for that grain to dry, because it takes time for the dry front to move from the bottom all the way to the top. The lowest profile there is giving you the node that is placed at the bottom of the bin. As you can see, because it is exposed to hot air fastest, that layer is going to dry the fastest. And eventually you are able to see profiles of the moisture content within the bin at different depths. Now, once that information is known, it is sent to a communication system, and that communication system essentially compares the moisture content within the bin and the ambient air conditions, and that gives us the capability to supervise the fan. We can turn on the fan or turn off the fan depending on the prevailing air condition. If the prevailing air conditions are such that they are going to re-wet the grain, we can turn off that fan. If the conditions are such that it's going to dry the grain, we can turn on that fan. And so here are a few capabilities that these new advancements within these systems have provided to us. We are able to intelligently monitor the grain moisture content and temperature, and also the air temperature and the relative humidity. And because of that, we are able to supervise the equilibrium moisture content of air that we are placing within these bins. We are also able to automatically control the fan, turn them off and on, depending on the air conditions, which eventually helps us in minimizing the drying energy cost that is associated with our on-farm bin drying. We are also able to remotely understand what's going within these bins via internet communication. We are able to receive email or text messages that can alert us of any potential problems, such as overheating, hot spots, or over-drying within the grain mass. Next, I want to describe high temperature dryers. These are very, very important, especially because of the short harvest window that we have for rice, and the fact that rice at high moisture content is very, very highly perishable. And so there are various approaches that are utilized in this drying, in this high temperature drying methods. Number one, we have in-bin batch dryers, we have recirculating bin dryers, we have continuous bin dryers, and then we have pass drying or cross-flow column dryers. I want to go through some of these step by step, beginning with in-bin batch dryers. So these are high temperature bin dryers. They have the same equipment as the natural air dryers, with addition of a high capacity heating unit. Typically, the preliminary temperature are usually set at about 113 degrees Fahrenheit. Now, the disadvantage of these dryers is that to get the grain on the top to dry, some form of over-drying will happen in the bottom layers, and over-drying is not something that is very entertained within the grain industry, because it results in loss of money. Our marketing moisture content for grain, especially rice, is about 13%. And so when we over-dry to about lower than those moisture content, we end up losing money because we sell it based on a weight basis. To be able to avoid some of this over drying, grain stirrers are installed in these bins. These are to allow uniformity of grain movement or uniformity of air movement within the grain mass. Unfortunately, what this does is sometimes they crush the grain, and when that happens, it leads to fissuring of those kernels, which eventually results in reduction of head rise yields. Now, the other method that I would like to describe here is the recirculating bin dryers. Again, these are bins filled with grain, and a fan and a heater is turned on. Typically, a sweep auger is placed at the bottom. That sweep auger is activated by the temperature or the moisture content of the grain. What this does is the grain that is closest to the plenum is moved to the top, and by so doing, the drier grain is moved to the top, the wetter grain is brought to the bottom, and that allows uniformity of grain drying as time progresses. Now, the problem with this dryer is that some rewetting of dry grain may take place, and this causes some inefficiency within these systems. Next, we have the continuous flow bin dryers. These have same bin setup as the recirculating bins, except in these cases, the sweep auger discharges the grain into a cooling bin. Typically recommended for low moisture grain, because in the cooling bin we don't expect further drying. We basically expect aeration or cooling of the grain without significant removal of moisture. And so again, these are cases where the heat is used to dry the grain at the drying front, and then it continues up the grain column, and that aids in the drying. I would like to describe next the pass or closed flow air dryers. Again, these are the most popular drying units within our Mid-South regions. They are the fastest method for drying grain. Most grain elevators use some form of pass dryer, and they dry large amount of grain very, very quickly. They require the highest energy inputs of all the drying methods. And they are called pass dryers because grain passes within this column that you can see in this diagram several times. As the grain passes, air is blown through it crosswise or perpendicular to the motion of the grain. And so you end up having some grain that is closest to the hot air drying faster compared to the grain that is farthest to the hot air. And this presents some challenges that I'm going to describe as we go further. Because the grain is moving in this column and is experiencing different heat depending on how far it is from the hot air side, you'd expect some non-uniformity of that grain as it passes through this column. And so because of that non-uniformity, we end up with under-drying and over-drying. And that brings the necessity of what we call grain inverters within this system to reduce that variability in moisture content of the kernels. This figure here illustrates the grain inverters. The figure A there is a case where we have the grain flowing through the columns without the inverters, and you'd have non-uniformly dried grains at the bottom. In figure B here, we have a case where we have the inverters installed somewhere midway within that column. And as you can see in this figure, because of the inverter, the position of the grain as it flows is changed as they come to pass through the inverter. So the grain that was initially closest to the hot air plenum moves further away, and the grain that was farthest to the plenum moves closest to the plenum. And by so doing, we are able to dry those grain uniformly as they go through the column. Again, because of the non-uniformity of the drying process within those grains, there is need for tempering, and this necessitates what we call tempering bins in this closed flow column drying setup. Tempering basically is a case where rice is held in the bins for a certain period of time as it goes through passes. And as the grain comes in, the grain at higher moisture content may need to go through this column several times. If it has lower moisture content, it may go through it once. But if it's a high moisture content, it may go through the column maybe 2 passes or 3 passes. Now, tempering process is necessary to allow the moisture gradients that are established as it goes through the column to subside. And when that happens, we are able to preserve this quality, the quality of the grain, in the sense that those moisture content gradients won't develop stresses that would eventually translate in fissure formation, that would eventually translate into breakage, that translates into head rise yield reductions. And so that tempering is very, very important to reduce those stresses within the kernels. Now, another thing that the tempering process does is that it improves energy utilization in subsequent passes, because when the moisture content equilibrates within that kernel, the subsequent pass is able to remove significantly larger amount of moisture from that kernel compared to if it was not tempered. I've mentioned this in passing, but in this slide here, I want to just show you some of the advantages and the disadvantages of these cross-flow column dryers. In terms of advantages, we are able to dry large volumes of the grain. The harvest rate can exceed the drying capacity. These systems provide the most control during harvesting and drying of rice. The disadvantages, on the other hand, is that the most expensive of all the drying options. You require addition of tempering and storage bins in these systems. Now, there are alternative technologies that have been developed or that are already in the progress of being developed, and these are brought about because of different needs within the rice industry. For example, we would like to dry rice faster. We would like to reduce things like moisture content and temperature gradients within the rice kernels. We also want to combat things like development of mycotoxins by inactivating some of the pathogenic fungi. We want to minimize moisture content gradients. We want to take care of insects that could be within this rice. And because of that, we need to come up with techniques that can dissipate a significant amount of energy on that rice within a short time, but at the same time not compromising the grain quality. In so doing, various techniques are being investigated, and this includes infrared dryers, microwave dryers, radio frequency dryers. The unique thing with these drying systems is that the mode of heat transfer is unique, is different from what we would have in our conventional systems that typically use convective and conductive mode of heat transfer. In these alternative techniques, they use more of a radiative heat transfer, and they tend to be a little bit more energy efficient in terms of heat dissipation from the source to the product. Now, with that, I want to leave you with the following references that you can go and look at and get additional information that can help you understand some of the elements that I've mentioned in passing in this module. Thank you very much for listening to this module number 6 on rice drying methods, and I look forward to developing more information as we go forward in the subsequent modules. Thank you.